Okay, so after we can derive this second order ODE and yeah, actually we can use our ODE knowledge to actually try to solve this ODE and then to see why the charge will be like this, and then also the frequency, why the frequency will become smaller than the original natural frequency. So let's see. Okay, so so for the first step, we try to change the second derivative to becomes s squared and then r over l, and then the first derivative becomes s, and then finally the original function becomes 1. Okay, so like this. So it becomes a second order constant coefficient. Second order algebraic equation. So in this case, as we have learned in high school, so we have 3 cases. Okay, so for the delta equals b squared over minus 4ac. Okay, so this is a is 1, b is r over l, and then c is 1 over LC. Okay, so yes, try to distinguish this C and capital C. Yeah, so b squared minus 4ac, yeah, it can have larger than 0, equals to 0, or smaller than 0. Okay, for the, for larger or equal, okay, so these 2 cases we will ignore. These 2 cases we will ignore. Yeah, because for the larger one, larger than 0, it means it becomes something like a times exponential to s1t plus b exponential to s2t. In this case, s1, s2 will be negative value, so it becomes 2 exponential function decaying. So it is not an oscillation, so that we will ignore this case. And even for the equal to 0 cases, equal to 0, it becomes a plus bt and then times exponential to negative s1t. Okay, it is not an oscillation either. Although this one is decreasing, this one is increasing, but yeah, as much as you have learned the Log-Bristol rule in calculus, you know that this one will still tends to 0 if t is large. So both of these 2 cases are not oscillating. So we will use we will only concern the most difficult case, which is delta is smaller than 0, which means here is r square minus l square is less than 4 over LC. Okay, something like this. Or actually this is equivalent to r square is smaller than 4L over C. Okay, we just move L square to the right side and then cancel with this L. So R square is smaller than 4L over C. So which means we hope this R to be small. We hope this R to be small enough so that this RLC circuit still oscillate. Okay, so in that case, if delta is smaller than 0, okay, according to the solution will be like S to be negative b plus or minus square root of b squared minus 4ac all over 2a. Okay, and then in that case, you just collect the real part and the imaginary part, so that S will be like negative. The first term will be negative b over 2a, okay, which is negative r over 2l, okay. So this is the real part, and then plus or minus the square root of b squared minus 4ac, b squared minus 4ac, Okay, which is actually this stuff, and then we try to rewrite it because this is a negative. This is a I mean R square over L square minus 4 over LC will be a negative value. So that turns out to be like a J times square root of 1 over LC minus R square over 4L square. Okay, so we divide by 4 because because this is like B square minus 4AC over 2A. A is 1, okay, A is 1, so still divide by 2. Okay, so if it is going into the, so it becomes a J square root of 4AC minus B square over 4, something like this, okay? So yeah, this is a little bit algebraic. I don't try to go through it as in every details. So, but it will be actually like this. Okay, so here we can still assume omega to be 1 over square root of LC, or omega square equals 1 over LC, which is this stuff. So this becomes omega square. So it becomes a negative R over 2L plus or minus J omega square minus this is nothing but R over 2L quantity square and then square root, something like this. So you can see, okay, so this is a new omega prime. Omega prime becomes square root of omega square minus R over 2L quantity square. So this is nothing but this one. Okay, so that's why the natural frequency with this resistor will be smaller than the original, with smaller than the natural frequency with only the LC. And finally, why it be like that? Because this is the solution. What we have learned is like Q will be like it should be like exponential to negative the real part. The real part will be negative R over 2L times L, so as times T. Okay, so this is the exponential to alpha T, this stuff is alpha, this stuff is alpha. So we have a exponential to alpha T, okay, will be like this. And then the remaining part is A cosine of omega prime T, okay. Omega prime is the imaginary part, A times cosine of omega prime T plus B sine omega prime T, okay. And similarly, okay, we have two cosine and sine with the same frequency. So actually we can write it as Q times exponential to negative RT over 2L, and then cosine omega prime T plus phi, okay, becomes this magnitude and a phase. So this is nothing but this one, okay, this one, Q times exponential to negative RT over 2L, and then cosine omega prime T plus phi. Okay, so we have already derived the equation 3124, 3125, 3126, and also 314. Okay. So so this is also another analogy to the spring mass system. So so we have let's say we have a spring, we have a mass, but previously we only consider the spring to be ideal, but here we also consider there are some friction, okay, there are some friction force. So the friction force The friction force is like a negative BV, okay? Negative BV. We just model it to be proportional to the velocity, and that the direction will be opposite to the velocity 啊，就是这个是这个是一个阻力的一个简单的模式。当然，实际你学那些什么什么摩擦系数的那些的话，就是有什么动摩擦、静摩擦啊，这个是简化到最简化的，它就是单纯跟这个速度成正比，但是方向相反的，这蛮符合想象的。因为阻力的话就是我往前走，我往前走的话，那阻力的话应该是往后的，阻止我向前啊。反之亦然啊，所以的话就是 negative BV 啊，or we can actually write it as negative B dx dt. Okay, v the velocity is the first derivative of the displacement. Okay, so here we still something like we have f equals negative kx and then also negative bv. Okay, so this is the total force, okay, including both of the spring, okay, negative kx according to the Hooke's law, and then the negative bv due to the frictions, something like that. Okay, so in this case it will be equals to ma according to the Newton's second law of motion. Ma is m d2x dt2. Okay, so in this case we can just divide m on both sides. So we have d2x dt2 plus k over m b over m, okay, b dx dt here. Okay, I can write like this: b over m dx dt, and then plus k over m x equals 0. Okay, so this is the second order ODE according to correspond to this spring mass system with friction. Okay, so compare with d2q dt2 plus r over l r over l dq dt, and then plus 1 over lc q equals 0. Okay, so so we just only need to correspond on this stuff to here, and then this stuff to here. So probably we change m to an l, and we change k to 1 over c, and then we also change b to r, and then also we change x to q. Okay, so yeah. So for all the equations, yeah, we can just make this substitution. Let's say for this, okay, let's say this one or this one like this. Okay, we can just change the variable like this, and then this equation will be suited for this spring mass system with friction. Okay, so yeah, so here we have another sample problem. So here it says a series RLC circuit has inductance L and capacitance C and resistance R. So and begins to oscillate at time t equals 0. At what time t will the amplitude of the change of the charge oscillations in the circuit be 50% of its initial value? Note that we do not know the initial value. No, that we don't. Amplitude of change. Amplitude of change. So we somehow recall the equation is like Q equals capital Q exponential to negative RT over 2L, and then cosine of this stuff. Okay. So we will say this stuff is the amplitude. This stuff is the amplitude. Amplitude. Okay, and it just tells you that we don't know what this stuff is. We don't know what this stuff is, and so this is an oscillation. We just ignore this part, and we just care about when the amplitude becomes half 50% means half of its initial values, which means Q doesn't change, so this stuff becomes 1/2. This stuff becomes 1/2. So when this stuff becomes 1/2, which means exponential to negative R over 2L T0. We hope to find this T0, okay, and then when it is 0.5 or 1/2, okay. So let's take lateral law and let's take reciprocal on both sides， 就是两边都取倒数那这个指数的话会变成正的，那这边的话会变成2 ，and then take log. Okay, so let's take the reciprocal on both sides and then take the log. So here we will have R over 2L T0 equals natural log of 2. So T0 is 2L over R natural log of 2. So we can substitute the values. 2 times 12 milli. 12 milli over R is 1.5 and the natural log of 2. So this is nothing but 11 millisecond. 11 millisecond. Okay, so in that case, the oscillation is something like this. Something like this. Something like this. Okay, so this one will be exponential to negative 2, RT over 2L. This one is actually negative exponential to negative RT over 2L. Like this. And then here we have a cosine. So it is somehow like we have an oscillation like this. Like this. Something. Okay, something like this. So we have some oscillation. The actual oscillation is the middle. Okay, so this is this one and this one. I should say this is Q. Q times this one. Okay, negative Q. Negative Q. Okay, so these two are the we will call it the envelope. The envelope. Okay, envelope 就是它的振幅会用这两条线去夹住它，那它在中间去震荡它在中间去震荡，我们会叫那两个叫做 envelope。那实际的震荡是中间这个像cosine的东西但是它的振幅被这个 exponential 衰减了所以它会越震越小。因为它的能量被那个 R 一直消耗，所以它的振幅会越来越小。Okay, and then for the question B, okay, how many oscillations are completed within this time? Okay, so first we would like to find omega prime to be omega square minus R over 2L quantity square, and then the whole square root. Okay, so this is nothing but 1 over LC minus R over 2L square, and then the square root. So we just plug in all the values. L is 12 times 10 to negative third, and then times C is 1.6 times 10 to negative 6, and then minus R is 1.5, and then over 2 times 12 times 10 to negative third, like this, and then square here, and then take the square root. Okay, so this is nothing but 7.217 radian per second. Okay, so this is the angular frequency. So for the number of oscillations will be 11 millisecond, 11 times 10 to negative third, and then times 7.217, and then over 2 pi, So we turn this one into the nominal frequency, the nominal frequency. OK， 就是这个是 frequency， 就是1秒会振几次，1秒会振几次。这个有2 pi 在的，就是 so it is like omega prime will be, or omega will be 2 pi f or 2 pi nu, depends on what variable you use. Usually I use f for the frequency, so we would like to know the f to be omega prime over 2 pi. Okay, so f times the t will becomes the number of period. Yeah, f times the t0, yeah, because f times t, okay, if it is the period, it becomes a 1. If it is omega t, it becomes 2 pi. Okay, so now we have f times, this is f, this is t0, so it becomes how many cycle? Okay, so this is a single cycle here. So this is 12.6 cycle. Okay, so cycle. Yeah, we don't need to put it in the unit. OK， 所以就是说它经过了12.6次震荡的话，但这个图画起来不是这样，就是如果这个是1倍，这个是0.5倍的话，哦，那它应该震荡的密很多，但是很难画。这个就是示意图，它大概是这样震的。Okay, so far any questions? Okay, so next, we talk about the phasors. Okay, so phasor is you can consider it's an easy part. But it is in some sense it's difficult to understand. Because what we would like to do here is for an arbitrary RLC circuit, not necessary to be RLC in series, it can be arbitrary any circuit with RLC inside. Okay, so here we try to provide a sinusoidal source or an alternating current source, AC source. Okay, 我们给它一个交流的电源，给一个可以有 RLC 元件的电路。And then we would like to find so-called the steady state. Okay, so with a RLC circuit, we provide an AC source. Okay, AC 的电源。And then we would like to find the steady state. Okay, 这个稳态。Oh, what does it mean by 稳态? Okay, so 稳态 means, of course, if you have a circuit, you can try to use the potential method to write an ODE. Okay, of course, for a single resistor circuit, it is not a differential circuit. It is nothing but V equals IR. So it is the easy case. But if we have capacitor or inductor, then we will have differential circuit. And as much as we have sinusoidal source, AC source is a sinusoidal source. Oh, it is cosine or sine, okay, but we will call it sinusoidal source. 一个正弦的 的输入正选的输入就是一个 an alternative current source, okay, AC source. Okay, so in that case, we will write a differential equation, constant coefficient differential equation, maybe first order, second order, or even high order. And then on the right side, the g of t will be a sinusoidal function. So according to what we have learned, okay, when we like to solve a constant coefficient ODE like this, we need to solve for the complementary solution and then try to define the particular solution as the combination of sine and cosine. Okay, so yeah, maybe I try to write it a bit, just one page before. Okay, so for an arbitrary circuit, okay, so with inductor and capacitor and also resistor, okay, a circuit. Okay, it doesn't necessarily to be a series RLC circuit, it can be arbitrary. Okay, so we can use potential method to write an ODE. Let's say it is something like d2v dt2 and then plus dv dt and then plus v to be 0, and then we have this one to be a1 a0, something like this. And then on the right side it can be something like let's say this is v0 sine of omega 1t, okay, something like this. Okay, so for the first step you need to solve for the complementary solution vct to be maybe it can be something like a exponential to negative s1t plus b times exponential to s2t, something like this. And then we also need to assume the vdt to be let's say c cosine of omega 1t plus d sine of omega 1t. Okay, and then we can solve for c and d, and then we try to add them together to be the complete solution. Yeah, but usually S1 S2 should be positive value if this circuit is stable. 就是如果这个电路稳定的话，这个 S1 S2 会是正数。那负 S1t 负 S2t 的话， so for negative S1t negative S2t, it will make this exponential function tends to 0 when t is large. Okay, so for the steady state, it means that when t tends to infinity or t is very large, when t is large, we will call this to be the steady state. Yeah, because the complementary solution will declare to be a 0. So finally, what remains is the particular solution, because it is a cosine or a sine, okay, and or a sine, okay. So it will just last forever, okay. So this is what we call the steady state. So, but the idea is that to solve the ODE like this is quite tedious, okay, quite tedious. So the circuit guys try to use something called a phasor. So it will try to make use of the complex number to represent a function, a sinusoidal function. Okay, because of a complex number, it has amplitude and phase. Okay, let's say it is a plus jb. You can represent it as a r to exponential j theta, something simplified like this. Okay, so this one can correspond to a sinusoidal like r cosine of omega 1t plus 5. Okay, but solving the function will be more complicated, but computing or calculating this complex number will be easier. So the physician or the circuit guys try to use the complex number, or we will call it the phasor, to do the stuff. Okay, it will simplify the calculation. But if you don't know the theory behind it, you will feel like, oh, it is strange. We use some complex number to calculate, and then we'll find out the real function as the solution. 就是这个是 phasor 中文我也不知道叫什么，反正他们就是用一些复数去代替掉一些元件它电阻会变成一个实数，电感会变成一个 J omega L 变成一个虚数 ，C 会变成1除以 J omega C， 也会变成一个虚数，然后它算一算并联串联算一算然后那个正弦波也会变成一个复数那你最后算出来的电压电流，它就会变成一个复数，它就会对应回来你先把那个时间的函数对应成一个复数，然后通过复数算来算去，当然复数算来算去比起算微分方程简单很多所以他们是希望做这样的转换转换成一个复数的一个领域里面，算完之后我再还原回来一个时间的函数那我就不用算微分方程，但是它背后的数学是什么？叫做 Fourier transform。Fourier transform。Fourier transform 它在不同的数学课本里面，它都有不同的形式。我们学 Signal and System 的话，就是ECE 或者是电机系学的 Signal and System， 它的 Fourier 转换的话，它会写成是这样的 exponential to negative j omega t dt， 从负无穷积分到正无穷，然后变成一个 xj omega， 它在一个时间的函数变成一个频率的函数。如果你还记得我之前讲过一个Laplace transform 的话，它是 xs 等于xt exponential to 负 st 负 st dt 从负无穷积分到正无穷，看起来蛮像的，它有蛮多东西是蛮像的，但是有一些东西是不一样的。往往我们会用到一个半变的 Laplace transform 是长这样的，从零积分到正无穷 xt ut， 然后 exponential to 负 st dt 那这个 ut 的话是一个 step function， 它等于when t is larger than 0 and then 0 for t is smaller than 0， 就是用一个台阶的函数，我们只看正的半边就是做这个 Laplace transform 跟这个有点像，但是又不太一样它的很多的 property 有点类似，但是又不完全一样反正也许你们以后会学到吧我只是稍微提一下。那背后有一些复杂的东西，比如说 Fourier transform 就不在这里讲所以的话你会觉得这里很难理解，但是你真的要算的时候，其实它也不复杂，你就是要算一些复数的计算Okay, so for the first case, it is a resistive load. You may consider this is very stupid, okay? Because for a resistor, it is nothing but V equals IR. We don't need to define so many stuff. But this is just a beginning. So we still want to include R in the phasor world, okay? So we still starting it like this, okay? So for the alternating EMF or the alternating current source, okay, AC source, okay? So we have E equals EM cosine of omega dt, okay? Omega dt. So this is the AC source. AC source. And then this AC source is just connected to a resistor only, okay? So this is very trivial. So this is plus or minus. So this is nothing but E. So for the VR here, it is nothing but E. So this VR is nothing but this. Okay, so feel like you define so many variables. So VR is nothing but E is EM cosine omega dt. And the phasor of the alternating potential is defined to be something like this. we still want to make the Ohm's law becomes V equals I out. So here, we will define this to be a V out cosine omega dt plus a phi, although here this phi is 0 degree. This phi is 0 degree. So in this case, we have V out to be the magnitude. Okay, not necessarily the magnitude, yeah. Because sometimes later you will find that this V out, the phasor of V can be a complex number, not necessary to be a real value 它这个 phasor 会是一个复数但是在电阻这个例子里面，它是一个实数。Okay, so actually you can somehow you can consider it is a plus 0 degree. So which means that I should say the V out, the phasor of V out, the phasor of V out t should be V out exponential to 0 degree or maybe 0. Okay, use the radian instead. Because you cannot put degree here. Okay, so this is the phase. Okay, although in this case the phase is 0. So exponential to 0 is nothing but 1. So you just feel like it is nothing but V out itself. And then maybe I should write it as a V out. Okay, V out. Okay, using another notation to write. Okay, V out is actually this V out 0. And then equals to the phasor of the I out to be capital I out. Okay, it's still a real value for the resistor, and then multiply by R, you may say why it is like that. Okay, also we can actually write it as I out to be EM over R, and then cosine of omega dt. Okay, so this is the current. The current as a time function will be V R over R, capital R. So it becomes EM over R times cosine omega dt. Okay, so here we just want to consider the complex amplitude or as the phasor to be V R equals I R times R. Okay? Because so we will just convert this V R to be EM to exponential to 0, and then so we will just consider the magnitude here, and then also the phase here to become the phasor of V R. Okay, also the IR is something like this. The amplitude here and also the phase here become the phasor. So it is something like a VR equals VR times cosine of omega dt, and then IR equals VR over R, and then cosine omega dt. And then here we actually define the impedance 中文叫做阻抗 the impedance of a resistor to be ZR to be R. Okay, so for the R is itself, but for L and C is not itself. So but still we would like to make it like ZR to be capital R. So far you feel like for the resistor it is just still that you just define something useless here, you feel like, but for the capacitor and inductor it is not the case. So for the capacitor, here, we have a capacitor here. So still we have the AC source to be eta equals EM times cosine omega dt. And then for the VC like this, VC is still the same EM cosine omega dt, cosine omega dt. Yeah, and then here for the IC will be C dVc dt. Okay, so we need to take the derivative. So VC go to here, and then cosine become negative sine. So we have negative sine omega dt. And then for the chain rule, we also have the omega d in the front, and then the C goes to here. So here we have omega d C VC sine of omega dt. Okay. Yeah, something like this. And we would like to keep this function to be cosine instead. So using the trigonometry identity, cosine omega dt could be cosine of omega dt plus pi over 2. Plus pi over 2. Yeah, so this is an identity in the high school trigonometry. Yeah, but also with a negative sign. So this negative sign, yeah, vanish, okay, or maybe absorbed by this transform. Yeah, because sine and cosine have a 90-degree phase shift. Okay, so you may also consider like let's say cosine for the first quadrant is positive, and then pi over 2 plus something. The second quadrant for the cosine will be negative. So absorbing this negative sign. Okay, so this whole thing become positive omega d C VC cosine of this stuff. Okay, so the idea is like the phasor becomes VC. Okay, this is still VC, exponential to 0 degree. Okay, the phase here is 0, is plus 0. Okay, but here we have plus pi over 2. Plus pi over 2. So actually, for the IC, the phasor of IC, okay, IC becomes omega d CVC, okay, which is this part. This part is the original magnitude, and then we need to include this phase to be exponential to I pi over 2. Exponential to I pi over 2. What is exponential to I pi over 2 is actually I or J, or J pi over 2. J pi over 2. So remember that J is square root of -1. Okay, so this is nothing but J omega d C VC. Okay, so here we try to define VC ZZ. ZZ is the impedance of the capacitor. Impedance of the capacitor is nothing but VC over IC. VC over IC. Yeah, VC to be VC. Okay, so in this case, we have VC. We move IC to the other side, and then we move J omega DC to the other side. It becomes 1 over J omega DC, like this. Okay, so here we just ignore this omega D, yeah, because at the beginning we assume the natural frequency or the signal frequency of the AC source to be omega D, yeah, but generally we can write it as 1 over J omega C. So it's just a notation. Okay, so this is impedance. This is the impedance of the capacitor, 1 over J omega C. Of course, you can write it as negative J over omega C, but yeah, we seldom do that. We always write it as 1 over J omega C. Yeah, so in this case, we have this expression, which is the phasor of V equals the phasor of I times impedance of the capacitor. So it is still have the form of the Ohm's law. 就是定义这个 impedance 的目的是为了这个 V 跟 I 还是满足这个 Ohm's law 的形式，但是这个 R 就变成一个 ZC 变成一个 impedance 所以为什么是 因为本来的话 ，R 等于 V 除以 I， R 等于 V 除以 I。那现在的话，我们定义的话是 Z 等于这个 phasor of V，phasor of V。phasor of V 除以 phasor of I 它就会变成一个 phasor 它就可以变成一个 impedance impedance of a capacitor, impedance of an inductor, an impedance of a resistor. But impedance of a resistor is the R itself. Yeah, but for the impedance of the capacitor, it is 1 over j omega c. 1 over j omega c. Okay, so let us finish also the inductor. So for the inductor, it's the same E equals Em cosine omega dt. And then for the I, we make it like IL to be IL times omega dt. So VL will be L di dt. VL will be L di dt. So it is nothing but, this is nothing but L di dt. So we put this one here. So the derivative of it becomes negative sine omega dt. And then IL goes to here, and then L goes to here, and then for the chain rule, omega d goes to here. Okay, and then also we change this sign into cosine. So cosine omega d plus pi over 2 to absorb this negative sign. And then similarly, okay, so here we have IL to be IL. And then this is for the VL. For the VL, it is nothing but omega d L IL, and then exponential to I pi over 2. Yeah, because this is pi over 2, so we have exponential to I pi over 2 here. So this is an imaginary number, so which is nothing but j omega d L IL. Okay. Like this. So here we can also define CL to be VL phasor over IL phasor. So this is nothing but moving this one to the other side. So we have J omega dl. Okay, so here we have CL to be J omega dl, or you can just ignore this D. Ignore this D is okay. So J omega L to be the impedance of the inductor. So in that case, we also have this VL equals IL ZL. So it is also like the general complex form of the Ohm's law. Okay, the complex form of the Ohm's law. So for not only for R, okay, but also C and L also satisfy the generalized Ohm's law, but we need to include the complex number. We can call it the phasor. We can call it the phasor or the impedance. Okay, or the impedance of the RLC. All of them will satisfy the generalized Ohm's law. V equals IR, V equals I times Z, V equals I times Z. Okay, so far we introduced the phasor, and also the impedance of RLC. If you feel like the mathematics is too much, okay, what you need to remember is only that, okay, so this ZR is R, and then also this ZC is 1 over J omega C, and then finally ZL is J omega L. So this is what you need to remember. Okay, you need to use it for the coming example, or even for the selected problem.